Check it out now, y'all.
nanoHUB-U, online instruction.
Okay, in the last lecture we talked about a very simple physical picture that helped us understand the current voltage characteristics of a MOSFET. What I want to do now is to do the mathematical derivation, following the traditional approach. And you know, we really have to admire these people in the 1960s who figured this out. They didn't have computer simulation programs. They couldn't look at the exact answer and determine what the appropriate approximations that were valid and could be made were. They had to understand the device deeply, decide what was important, figure out how to simplify it, and develop analytical approaches. And they did a wonderful job. In fact, this is still the textbook treatment of the current voltage characteristics of a MOSFET. But we're really pushing the limits of this approach these days with these extremely small transistors. And the parameters in this model are losing their physical significance. So that's what this course is all about, but we want to begin the course with understanding the traditional way that people compute the IV characteristics of MOSFETs. Okay, so here's our circuit schematic for a MOSFET. By convention, people like to define the positive direction of drain current, not necessarily to be in the positive X direction, but to be in the direction of flow into the drain terminal of the MOSFET. Okay. So these are our typical IV characteristics. We have a linear region where the device operates like a gate voltage controlled resistor, and we have a region where the current is more or less constant and the device operates like a gate voltage controlled current source. Now, you can calculate the IV characteristics over the whole regime, but that gets a little bit mathematically involved. So all I'm going to do in this lecture is just try to calculate the IV characteristics in the linear regime and then in the saturated regime separately. Okay, and we'll get an expression for the on current in the process of doing this. Okay, so let's dive into it. So here's our cartoon sketch of a MOSFET. We remember that current is basically charge times charge per unit time, and it ends up being written as charge in coulombs per square centimeter in the channel times the average velocity of electrons flowing in the channel times the width of the MOSFET in the direction coming out of the board here. And the minus sign here is just because of the sign convention that current is positive when it flows in the drain terminal. Okay. Now you'll recall that capacitance is defined as charge divided by voltage. Now we're going to be talking next week about MOS electrostatics in quite a bit of detail, but I'm just going to give you a result here now that I'll ask you to accept on faith for the time being. We could solve this equation and it would say that charge is capacitance times voltage. But we're not interested in the total charge here. We're interested just in the charge due to the mobile electrons that carry the current and flow from source to drain. And there isn't any charge until the gate voltage is big enough to create that channel and lower the barrier so electrons can hop over and get into the channel. So the way we write the charge is the charge in coulombs per square centimeter is negative because they're electrons. It's a capacitance per unit area, that's what Cox is. And then it's times the voltage on the gate, but it's the amount of the voltage that's above the threshold voltage to create the channel in the first place. So it's V gate to source minus the threshold voltage. So below threshold, we're just going to assume that there is no charge. That's not quite right. We'll have to fix that up later. And the definition of this oxide capacitance, it's just a parallel plate capacitor. And the capacitance per unit area is just the dielectric constant of the oxide divided by the thickness, Tox, of the oxide, which is in the range of 1 to 2 nanometers these days. Okay, so if we accept this MOS electrostatics on faith until we talk about it in more detail, then we have enough that we can compute the IV characteristics of this device. All right, so let's look at the low drain to source voltage region first. So we're going to begin with this expression for the charge in the inversion layer. It's just Cox Vg minus Vt. Then we'll take our expression for current minus width of the MOSFET times charge per square centimeter times the average velocity that those electrons are flowing. Okay, we have a simple expression for the charge, and we've seen that if there's a constant electric field in the channel, and we saw from the energy band diagrams in the last lecture that there is under small drain to source voltage, then the average velocity is just minus mobility times the electric field. Okay, the electric field is just the voltage across the channel, which is the drain to source voltage, divided by the length of the channel L. And it's pointing in the minus X direction from the drain to the source. So all we have to do is to put all of these together and plug them in our expression for the drain current, and we get a very simple expression for the linear regime current. So this is a textbook expression that you see in every textbook on MOS transistors. The linear region current is width of the transistor divided by length of the transistor times the effective mobility times the oxide capacitance times Vg minus Vt times the drain to source voltage. I should point out that the mobility of electrons in the bulk can be quite high. The effective mobility refers to the mobility of electrons up here in this channel at the surface. And that can be quite a bit lower, a factor of 2 or more lower, because of the roughness of the surface. Electrons bounce off that roughness and they can't move quite as fast. Okay, so we have our expression for part of the IB characteristic. Now let's look at a higher drain to source voltage, and here it takes a little bit more care. The voltage in the channel at the source end is 0 if I ground the source, and at the drain end it's the drain voltage, and it varies continuously. Now what's important in inducing charge in the inversion layer is the amount that the gate voltage is above the voltage in the channel, V of X, and that all has to be bigger than Vt. Now when I applied a small drain voltage, I just said the voltage in the channel is essentially 0, and I ignored this term. But as I apply larger and larger drain voltages, I have to take that term into account. Okay. In fact, things can happen if the drain voltage is big enough that the drain voltage is Vg minus Vt, then this expression will tell me that I have no charge at the drain end of the channel. Well, if I have no charge, I'll have no current. So that's not quite true, but what it means is that I have a very small charge and a very large electric field that's carrying the current. And this is a regime that we would call pinch-off. Okay, so let's take that and see if we can use that basic picture and understand how this transistor operates. Now, let me first of all just mention quickly what pinch-off is, because this is something that tends to confuse people when they see it the first time. So the idea is that, we'll explain it in terms of energy band diagrams, because that always gives us a very physical way to explain anything related to semiconductor devices. Remember that the conduction band varies when the potential in the semiconductor varies, and that the gradient of the electrostatic potential minus the gradient is the electric field. So the slope of the energy band diagram gives me the electric field. So if I look at these numerically computed energy band diagrams under high voltage between the drain and the source, you'll see that I have a small electric field near the source, but I have a very high electric field near the drain. Nothing really magic happens at pinch-off. The pinch-off point is occurring about here. This is the region where the electric field gets very high. That means it takes very little charge to carry the current. The charge is essentially 0, and we would call that pinch-off. But you can see the current isn't going to stop. Electrons hop over the small barrier, they flow across the source, they see the strong electric field, and they just get swept out the drain. So that pinch-off region doesn't stop current flow, it just allows it to continue to flow. All right, so with that, we can dive into seeing if we can compute the IB characteristics under high drain to source bias. Okay, so under these conditions, there's a part of the channel that we lose. The actual channel goes from the source end to the point at which the voltage is big enough that the charge essentially goes to 0. After that point, the electric field is very big, it just sweeps everything out, and it really doesn't limit the current in any way. So our channel doesn't quite go all the way across, if I think of the channel as the part of the device where we have a high electron density. Okay, I'll begin with my same current expression, and I can evaluate this now anywhere. Under small drain to source bias, it really didn't matter because everything was the same everywhere in the channel. Under high drain to source bias, the velocity is changing very much when I go from the source end to the drain end. So I have to pick carefully where I want to calculate the current. I'll get the same answer everywhere because current is continuous, but I want to pick the point where it's easiest to compute the current. And that point is at the beginning of the channel where x equals 0. So that's where we'll compute the current. Because at x equals 0, the potential in the semiconductor is 0. So the charge is just minus Cox, Vg minus Vt. There's no voltage in the semiconductor to subtract. The average velocity at that point, well, there's an electric field at that point, so the average velocity is minus mu times the electric field. And now we have to ask ourselves, what is the electric field? It's not the drain to source voltage divided by the channel length, which it was for the small drain to source voltage. It's not that because the electric field is highly nonlinear. But the way we can get it is to remember that the voltage at the end of the channel is Vg minus Vt. That pinch-off region is very small, so the length of the region over which that voltage drops is still about the channel length. So the electric field at the beginning of the channel is the voltage at the end of the channel minus 0, the voltage at the beginning, divided by the channel length. It's now Vgs minus Vt divided by L, instead of the drain voltage divided by L. Plug all that together, and we get an expression that's called the square law expression for the MOSFET. So the current is W over L, mobility times oxide capacitance times Vgs minus Vt squared. The squared occurs because one Vgs minus Vt relates to the charge, and the second Vgs minus Vt brings in this pinch-off point and determines the lateral electric field. And now if I do this a little more carefully, there's a factor of 2 I've lost because the electric field is non-uniform. What we've done is to compute the average electric field. It's actually a factor of 2 lower right at the source where we're evaluating the current. But the important point is that we have the textbook square law description of the MOSFET, which should describe this region in which the device is a gate voltage controlled current source, but we've got a very big problem. This expression says that the current should increase as the square of the gate voltage as I increase the gate voltage, and you can see that that is not occurring. The current is increasing linearly with gate voltage. So something is wrong here. You know, I've been looking at transistors for quite a few years now, and I've never seen one that behaves according to this square law behavior. So we've missed something. You know, what have we missed? So this is where traditionally we'll bring in velocity saturation. If I have a large chunk of silicon and I apply a very high electric field, the velocity will no longer be proportional to the electric field. It will saturate as I get more and more scattering, and it will saturate at about 10 to the 7th centimeters per second. Okay. So under high drain bias, the question is, are we in the region where the velocity is proportional to the electric field, or are we in the region where the velocity is independent of electric field? Well, we did this in the lecture on transport. You know, you just do some typical numbers for a present-day MOSFET, and what you'll find is that the electric field is very, very high. We would expect to be in this regime where the velocity is independent of the drain to source voltage, clamped at 10 to the 7th centimeters per second in silicon. So let's go back and use that and see if we can redo the IV characteristics accounting for velocity saturation. We begin with our drain current expression. We will evaluate the charge anywhere in the channel, but let's pick 0. But now since the velocity is going to be constant in the channel, things are going to be the same anywhere in the channel. So the charge is minus Cox, Vg minus Vt. And now the average velocity is very easy. It's just Vsat. We will assume that the field is so high everywhere in the channel that the electrons are just moving at 10 to the 7th centimeters per second. Right, so now plug this into our expression, we get a very simple expression. the drain current is width times Cox times the saturated velocity times Vg minus Vt. And that's exactly what we observe experimentally, that the current increases linearly with gate to source voltage. In fact, people will typically say that, people will typically look at these IV characteristics, and when you see a linear increase in current with gate to source voltage, people will call that the signature of velocity saturation. That's telling you that you're dealing with a velocity saturated MOSFET. Okay, so these are also textbook descriptions. This is the way people have thought about this problem for a long time. What's this course all about? What more do we need to say? Well, remember when I talked about transport, I showed you some computer simulations from the IBM group several years ago, which were looking at channel lengths that are now bigger than current day state-of-the-art technology. And they were simulating electron transport from the source across the channel and out the drain. And we showed that we could look at the velocity in this device, especially at the region near the drain where the electric field is very high, and we could see if it saturated at 10 to the 7th centimeters per second. And this is the result of that simulation. And the point was, there's no hint of velocity saturation. In these small devices, contrary to a large bulk piece of silicon with a high electric field, the velocity does not saturate, very simply because the electrons don't have time to scatter very much. They're out the drain before they can scatter enough time to lower their velocity to Vsat. So that kind of high field velocity saturation that we are familiar with in bulk semiconductors just doesn't occur in these small devices. So this is a mystery. This is something that we're going to have to understand why the IV characteristics suggest that there is velocity saturation going on, and how we relate that to our physical understanding of carrier transport in small devices, which says that the velocity overshoots, it doesn't saturate. But we'll get to that later in the course, and we'll see that it's not too hard to understand. Okay, so let's recap what we've done. We've looked at the traditional way that people think about the current voltage characteristics of MOSFETs. We've developed an expression for the linear regime current that is very simple and easy to derive. We've developed an expression for the saturated region current that is very simple and easy to derive, especially if we assume velocity saturation in high electric fields. You know, there are some details that we're going to need to talk about what is this slope all about in the saturated regime, how do we smoothly connect the two. But we've got the basic picture with this two-piece model. Okay. So we can think about this model as then being, we have a critical voltage, and the way we think about this is whichever current is lower is going to be the current that matters. So there's some critical voltage where these 2 points intersect. We'll call that VDSat. And below VDSat, which is just given by equating those two currents, the value of VDSat is the saturated velocity times the channel length divided by the effective mobility. We have expressions below that VDSat and above that VDSat. So we simply look at when we compute the IV characteristics, if we're using a drain voltage that's below VDSat, we use the expression for the linear regime current. If we're applying a drain voltage that's bigger than VDSat, we use the drain current in the saturated regime. And we have an abrupt transition then in this two-piece model between the two regimes. Okay. Now, we can improve this model. But there are a couple of things that we're going to have to discuss here in a little more detail. The model that we have outlined here now in this lecture is really only valid for very long channel transistors. It was very firmly physics-based in the 1960s and the 1970s and even in the early 1980s. But we have pushed channels to such small dimensions that the physical principles of this drift diffusion, saturated velocity transport just no longer apply. And that's because mobility is a concept that only makes sense when the channel length is many mean free paths long And as we've seen from the detailed transport simulations, velocity doesn't saturate in these high electric fields in these short channel devices. So there's some interesting physics that we're going to have to describe, but one of the things that is very interesting is that people still use this model. And it still does a good job of fitting the IV characteristics if we think about these parameters as empirical parameters. If we can adjust the mobility and the saturated velocity just a little bit, we can fit the IV characteristics of a MOSFET. Now it's interesting to ask why that is. And the reason is that fundamentally a transistor is a barrier-controlled device. The shape of the IV characteristic comes from this manipulating potential energy barriers with voltages. Now the actual magnitude of the current comes from the particular way that we treat transport, but the shape doesn't really change very much. So we get the right shape of the IV characteristics even though we have the wrong transport physics. And people can empirically adjust some of these parameters and still describe transistors. Now what we want to do in this course is to show that if we think about this device in the right way, we can still understand it very simply, and we can attach very simple, clear physical interpretations to these parameters. They no longer are empirical parameters that are just adjusted to fit the IV characteristics. Okay, so before we do that, the next step that I want to do is to take this very simple two-piece model and show you how people have extended it into a realistic semi-empirical model that describes MOSFETs today. And then as the course develops and we go beyond, we'll go back to this model, which was developed at MIT and is called the virtual source model. We'll go back to this empirical model and we'll make it more and more physical. And that's really what this course is all about how we establish a very physical but simple and easy to understand model for these short channel transistors. So we'll dive into the virtual source model in the next lecture. Thank you.